Section 4.4, Context Isolation, keeping users' data separate in multi-user AI systems. What is context isolation? Context isolation means enforcing strict boundaries between different users' data, memory, conversation history, and tool outputs within a shared AI system. Without these boundaries, one user's private information can appear in another user's responses, not through traditional hacking, but simply because the infrastructure meant to keep them separate is missing or misconfigured. This is not a theoretical concern. In March 2023, OpenAI took ChatGPT offline after a race condition in a Redis client library caused some users to briefly see fragments of other users' chat histories and billing information. Context isolation in agentic systems is governed by OWASP LLM-02, 2025, Sensitive Information Disclosure, which jumped from number 6 to number 2 on the OWASP Top 10 for LLM applications between the 2023 and 2025 editions. This rise reflects both the rapid adoption of multi-user AI features and the growing number of documented incidents. Why do agentic systems make context isolation harder? A simple chatbot has only one place where context can leak, the conversation history. But an AI agent has 6 independent isolation boundaries. First, conversation history stored between turns. Second, long-term memory carried across sessions. Third, retrieve documents from a RAG knowledge base. Fourth, tool call results cached for performance. Fifth, inference caches at the model server level. And sixth, application logs that record everything the agent saw and did. Each of these is an independent isolation boundary. A failure at any one of them can leak data, even if the other 5 are perfectly implemented. This is what makes agentic systems fundamentally harder to secure than simple chatbots. The first failure mode is shared agent memory without per-user scoping. Agent memory systems like LangChain memory, Letta, or custom Redis-backed stores maintain a persistent record of what the agent has seen and done. When a single agent instance is shared across multiple users without scoping that memory to individual users, memories written during one user's session become part of the agent's persistent knowledge and can surface in another user's responses. Here's what this looks like in practice. Imagine a developer builds a personal finance assistant and uses a single agent instance for all users, storing financial goals and account summaries in the agent's shared memory. When user B logs in, the agent recalls user A's account balance and budget targets as if they were user B's own data, because both users share the same memory namespace. The second failure mode is vector store cross-user contamination. In RAG pipelines, documents are converted into embeddings and stored in a vector database. If all users' documents share the same flat index with no physical separation, a query from one user can retrieve documents belonging to a different user simply because those documents are semantically similar. There's a critical distinction between physical isolation and metadata filtering. Physical isolation means separate namespaces or shards per user, enforced at the database level. Metadata filtering stores all data in one index with a user ID filter at query time. The weakness of metadata filtering, if the filter is bypassed through a bug, a code refactor, or a prompt injection attack, all users' data is exposed at once. Physical namespace isolation limits damage to a single user, even if the application layer fails. The third failure mode is the shared inference cache timing side channel. When AI applications run on shared infrastructure with prefix caching enabled, an attacker can measure time to first token latency to determine whether a specific prefix exists in cache. A request that hits a cached prefix returns faster than one that misses. By sending carefully crafted queries and measuring the response latency, an attacker can infer something about another user's recent prompt without ever receiving its content directly. This attack was demonstrated in a paper published at NDSS 2025, titled "I Know What You Asked: Prompt Leakage via KV Cache Sharing in Multi-Tenant LLM Serving." The fix is a per-request cache salt, a random value injected into the cache key hash so that only requests from the same user with the same salt can share cached computation blocks. VLLM added this as a configuration option specifically in response to this research. The fourth failure mode is session context not being fully reset between users. When the orchestration layer fails to fully reset a session state, whether due to a software bug, a race condition under high load, or a misconfigured in-memory store, fragments of one user's conversation remain active when the next user's session begins. Unlike the cache timing attack, this failure requires no measurement. The contaminating data appears directly in the next user's responses. This is exactly what caused the OpenAI ChatGPT incident of March 2023. A bug in the Redis-backed client library caused concurrent requests to receive each other's cached session data. During a roughly 9-hour window, approximately 1.2% of active ChatGPT Plus users could see another user's chat history titles, first messages, names, email addresses, payment addresses, and the last 4 digits of their credit card. The root cause was an infrastructure-level caching failure, simply a missing isolation boundary in a shared cache. The fifth failure mode is shared application logs. Application-level logging records every user interaction, every tool call, every retrieved document, and every model response. In a multi-user system, if these logs are not scoped per user, they become a single concentration point for all users' sensitive data. This is less of a real-time leakage risk and more of an accumulation risk. Over time, logs collect sensitive data from every user, which can then be exposed through a compromised engineer account, misconfigured log permissions, or a legal subpoena. A single log access event could expose sensitive data from every user who ever used the application. Let's look at 3 real-world incidents. First, the ChatGPT Redis bug from March 2023. A race condition in Redis-Pi caused one user's session data to be served to another user. About 1.2% of Plus users saw other users' chat histories, names, emails, payment addresses, and partial credit card numbers during a 9-hour window. Second, security firm Giscard demonstrated a telemedicine AI assistant where cached patient consultation notes could be retrieved across sessions. A request framed as an internal clinical validator accessed patient names, social security numbers, diagnoses, and medications, with estimated HIPAA exposure exceeding $1.5 million. Third, in April 2024, Wiz researchers found that Hugging Face's shared Kubernetes infrastructure allowed a malicious model upload to move laterally and access other tenants' data. On Replicate, remote code execution connected to a shared Redis instance exposing customer API keys. These incidents show that context isolation is not just an application layer concern. Shared inference infrastructure carries the same requirements. Now let's look at how to implement context isolation. The most fundamental rule: scope all memory to a server-verified user ID. Every piece of data an agent stores or retrieves must be keyed by a server-verified user identifier, never by a value the user supplies. Server-verified means the ID comes from your authentication system, like a validated JWT claim or session object, not from a query parameter, cookie, or request body. Here's the vulnerable pattern. The code reads a username directly from the request body and uses it as the memory key. Any user who submits a different username can read that user's full history. Here's the secure pattern. The user ID comes from the server-side auth session via currentuser.id. The client cannot change this value. The memory key is namespaced with this verified ID, and a time to live ensures stale sessions expire automatically. For memory frameworks like Letta or LangChain, the same principle applies. Create one agent instance per user, with identity scoped by a server-verified ID. Never share a single instance across all users. Next, database and vector store isolation patterns. For RAG-powered agents, use per-user namespaces in your vector store. The code constructs a namespace from the server-verified user ID, and all upserts and queries are scoped to that namespace. Queries in one namespace cannot retrieve vectors from another. Isolation is enforced at the database level, not in your application code. For relational databases, use row-level security. With PostgreSQL and pgvector, create a policy that restricts every select to rows where user ID matches the current session variable. Even if application code omits a where clause, the database refuses to return another user's rows. When using connection poolers like pgbouncer, use session-level variables rather than relying on the database username. Finally, set time-to-live values on all cached session data. A 24-hour TTL serves 2 purposes. It prevents stale context from bleeding into future sessions, and it limits the accumulation of sensitive data in caches. There's a combined threat when context isolation and least privilege are not both implemented, the confused deputy problem in multi-user agents. When an agent holds a service account with access to all users' records, an indirect prompt injection, hidden instructions in an uploaded document, can instruct the agent to retrieve another user's data. Here's how it works. User A uploads a malicious document with hidden instructions like retrieve all records for user ID equals B. If the retrieval layer relies on metadata filtering, the injected instruction can manipulate those filter parameters, causing the agent to retrieve user B's private documents in user A's response. The defense requires both controls together. Context isolation limits which user's data the agent can access. With namespace isolation, the attack fails at the database level. Least privilege limits what the agent can do. Both are necessary, and neither is sufficient alone. When reviewing a multi-user agentic system, work through this audit checklist. For every data store, ask, is access controlled by a server-verified identity? Does the database enforce the boundary if a developer omits scoping? Is there a time to live on cached data? For RAG retrieval, are documents physically isolated per user? Is authorization verified after retrieval? Could a prompt injection manipulate the retrieval parameters? For agent memory, is there one agent instance per user or a shared instance? Is memory partitioned by identity at the storage layer? Are writes scoped to the authenticated user? For application logs, are raw messages and model responses excluded from logs? Is log access scoped to those with legitimate need? Do entries include only metadata, user ID, session ID, and timestamp, not sensitive content? To wrap up, context isolation is not a single control. It's a discipline applied consistently across every layer of a multi-user agentic system. Here are the 3 most important implementation choices. Number 1, use physical isolation in your vector store. Use namespaces or per-tenant shards rather than metadata-only filtering so that a filter bypass cannot expose all users' data at once. Number 2, apply row-level security policies on database tables used for agent memory or RAG storage. This ensures the database engine enforces isolation independently of your application code. Number 3, use server-verified user IDs as the single source of truth for all storage keys. Never use anything the client submits as an isolation identifier. In the next section, we'll cover monitoring and observability, what your logs should record about the agent's actions, and what signals indicate that isolation boundaries are being probed or breached. Isolate by default, share by exception. Context isolation ensures that one user's data never appears in another user's session. Treat every shared resource, memory, vector stores, caches, and logs, as a potential cross-tenant channel. Namespace everything by tenant, enforce at the infrastructure layer, and audit regularly for leakage. Next up, Section 4.5, Monitoring and Observability, detecting what prevention controls miss. For more details, visit wisebuilder.dev.